Okay, so it's very pleasant, very nice to be here. Thanks to the organisers. So just firstly, to avoid any misunderstandings about the title, this is a project. This is very much work in progress. We're trying to make quantum gravity from non-commutative geometry. I haven't come here to tell you all about exactly how to do it, but I want to explain what we've done so far and where we are on this kind of project. So, rough outline, I want to talk about finite real spectral triples, which is the technical gadget. And particular examples are called matrix geometries. And there's a little interlude in the middle where I talk about the fuzzy sphere as an example, and the difference between trivial and non-trivial bundles. And then finally, I get to describing quantum gravity. So it's not just one geometry, but some kind of sum over geometries. And as part of that, I'm going to talk about the Fermion integration at the end. Okay, so firstly, here's a picture of space-time. It's by Georges Seurat. And it's a scene, a continuum scene, you'll agree, of macroscopic objects. But if you look very carefully at the canvas, you magnify it a bit, it isn't a continuous drawing. It's made up of small points. It's the pointillism. And so on the canvas, there's a finite number of dots making this picture. So this is the sort of picture of space-time we expect from non-commutative geometry, that at small scales, there isn't the resolution of the points infinitely well, that the non-commutativity starts to become important, and points are kind of smeared out, a bit like in quantum mechanics, I guess. Whereas on a large scale, you see something that behaves at low energy like ordinary continuum physics. So if you like, this is the first non-commutative piece of art. So the technical gadget is a real spectral triple, and I'll run through this very briefly. So there's a star algebra A. H is a bimodule over A. So there's a left action and a right action, they commute. D maps H to H. There's a typo there. So it's a self-adjoint operator on the Hilbert space, H. J is an antilinear map on the Hilbert space, and it has various properties, which I'll talk about in the next slide. But particularly,
John, D is from A to A?
H to H, that should say. And that's the light, yes? Yeah, oh, right. Oh, no, it's not, it's a pointer. Okay, so the property on the right there, J interchanges the left and the right actions of the bimodule. And finally at the bottom there is gamma, which is the chirality operator. So it squares to 1, so it has eigenvalues plus or minus 1, which are the left-handed and right-handed fermions. So the fermions are the things living in curly H, the Hilbert space. And on the right there you see that D commutes or anticommutes with the chirality operator depending whether it's odd or even. Finally at the bottom here there's this very important first order condition, which is if you take the double commutator of the Dirac operator with the left action by some algebra element and then the right action by some other algebra element, you get 0 for any two algebra elements. And this is the non-commutative generalization of the condition that the Dirac operator is a first-order differential operator on a manifold. On a manifold, you have a commutative algebra, and the left and the right actions are the same. And then this condition just says that if you commute with a function twice, you get nothing, which is, of course, tells you it's a first-order differential operator. Okay, so I guess this is fairly familiar to most people, but so here's the KO dimension, the final piece of the jigsaw, the properties of the antilinear operator J, called the real structure. and it squares to plus or minus 1. It commutes or anticommutes with the Dirac operator, and it commutes or anticommutes with the chirality operator. And those signs arrange themselves in a table there, which tell you the parameter S, which is the KO dimension of the spectral triple. Now, these signs and these properties are exactly the same for a Clifford module. You have a Clifford module for a real Clifford algebra, then you have likewise a chirality operator and a real structure called charge conjugation, and they have the same relations here, where you just put in, for D you put in a gamma matrix, and gamma, big gamma is the chirality operator, and you have the same table of signs for a Clifford module. So, in fact, examples of spectral triples are built with Clifford modules. There's no surprise that the same algebra occurs there. Okay, so important examples of real spectral triples. So the first one is if M is a spin manifold, and then the algebra of functions on that you can then use as the algebra in a spectral triple, and the Hilbert space is the Hilbert space of sections of the spin bundle, and the Dirac operator is the Dirac operator. The second example is the internal space of the standard model. So you take all the fields in the standard model on your space-time, and at one particular point, you can arrange all those fields together, all the bosonic fields together, into an internal space. And the Hilbert space is the Hilbert space at one point of all the Fermion species, all direct summed together. And that internal space has a Dirac operator on it, which is made from the coupling constants and the Higgs fields, and that's the standard model internal space. And it was a very important discovery of Alain Connes that this forms a real spectral triple. And in fact, that was part of the development of the whole notion of a real spectral triple, is discovering that the standard model is an example. So, so that's, from the sort of physics project point of view, very important. And then the idea of Connes was to take the product of the space-time manifold, which I always think of as sort of horizontal in the internal space, sort of vertical, take the product, and that's the standard model vacuum. There's space-time geometry and some geometry for the internal space. And that describes the standard model. So this spectral triple M cross F is called an almost commutative spectral triple because it's commutative in the manifold direction and non-commutative in the internal space direction. But from the point of view of sort of physics, that's a sort of very funny thing to have one thing be commutative and the other thing, and infinite dimensional Hilbert space and everything, and the other thing to be non-commutative and finite dimensional Hilbert space. So why don't we make them both the same? That's the project. So let's replace the manifold with a finite non-commutative real spectral triple and see what happens. And in the process, of course, things simplify in one sense, that everything, because you're dealing with finite dimensional matrices, everything becomes commutable. And from the point of view of doing the quantum theory, that's a huge, huge bonus. Having spent most of my life working on quantum gravity in various schemes that involve huge infinite dimensional spaces with series that don't converge and are uncontrollable, to suddenly have something that, oh, you can put this on a computer and get a number out. It's just sort of fantastic. Okay, so let's now look at some examples of real finite spectral triples. Simple examples, which the algebra is just simply a matrix algebra. MNR means the n by n real matrices. Or you can have Mn over 2H, which you think of as n by n complex matrices by replacing each quaternion by a 2 by 2 complex matrix. So they both act on a Hilbert space of Cn. But you want a bimodule, so you don't just want Cn, you want Cn tensor its dual. So you have the matrices MNC as part of the Hilbert space. In fact, these, just M and C itself, it would be a bimodule over either of these algebras. But we tensor by CK. And CK is a Clifford module, so type PQ, meaning there are P gamma matrices that square to +1 and Q that square to -1. And then the left action and the right action are very simple. The left action is written here, and it doesn't point, does it? No. Okay. So the left action is you just multiply the algebra element as a matrix on M in the Hilbert space on the left. And the right action is matrix multiplication on the right, not surprisingly. The real structure is the charge conjugation on the spinor, tensored with the Hermitian conjugation on the matrix. Simple. And the chirality operator is the Clifford module chirality operator, just acting on the spinor part. So this is a very simple sort of matrix geometry. What you think of is that the MNC is sort of the complex functions on the space, and tensoring with CK is giving yourself global spinors. So it's a spinor bundle, but it's the same fiber everywhere on the space. So it's a trivial spinor bundle on this space. And that's a very simple thing to do, but it's also somewhat naive and possibly missing something. Yes?
Is A, the representation of A on H doesn't affect the Clifford module?
It doesn't act on the Clifford module, exactly, yes. That just acts on the matrix part. Yeah.
Why do you exclude complex numbers?
I want a real algebra because the standard model in term space is a real algebra, so I want...
Complex algebra is also a real algebra.
Oh yeah, right, sorry, yes, that's also a case, yeah. You can have MNC considered as a real algebra, yes, you're right, thank you, yes. I missed that off, yeah. That's quite right. Okay, and then the thing I haven't told you about is the Dirac operator. And these get more complicated as the size of the Clifford module increases. The P and Q integers get larger. But here are the first few cases. The 0, 1 and 1, 0 are just commutators or anti-commutators. The curly brackets are anti-commutators. So 1, 0 is anti-commutator with H, a Hermitian matrix. And the L's here are anti-Hermitian matrix. So the 0, 1 is, in fact, because the gamma matrix is I, it's just the commutator with a Hermitian matrix. When you get the two-dimensional ones, 0, 2, 1, 1, and 2, 0, there are two terms. There are two gamma matrices you have in this Clifford algebra. And so the gamma matrices obviously act on the Clifford module part. Yeah, so in 0, 2, both gamma matrices square to -1, but they have different meanings in the other cases. Yeah. So in 1, 1, gamma 1 squares to +1, and gamma 2 squares to -1. So the whole thing is Hermitian, you see. And the one at the bottom, the 0, 3, I'm going to use a fair bit later on. So that has one Hermitian matrix, it's the anti-commutator with that, and then 3 commutators with anti-Hermitian matrices, which, by the way, you should think of as like the derivatives. So a commutator with an anti-Hermitian matrix is a non-commutative version of a derivative. So that's
0, 3 or should be 1, 3?
That's 0, 3. So that has 3. You can think of this sort of in a sort of naive way as having 3 derivative terms, L1, L2, and L3 commutators, and the H term is like an order 0 operator. It's like the spin connection coefficients part of the Dirac operator. Okay. So here's an example of a geometry that we all know and love. Anybody doing this kind of stuff? starts with the fuzzy sphere. So here it is. And the fuzzy sphere as a matrix geometry is you take two-dimensional spinors and tensor with MNC as the Hilbert space. And the Dirac operator was written down by Grosser and Presnada in 1995. It's type 03, and therefore has K dimension of 3. And the formula is one of the types I had on the previous slide. It's at the bottom here, where the Hermitian matrix H is just in fact a half, so the anti-commutator is just 1. And then there's the three L1, L2, and L3 are the generators of the representation of SU2, of the n-dimensional representation. So the Li here, perhaps I should have written on the slide, these are now generators of SU2, the symmetry of this sphere. Okay. And the algebra you can write as MNR or MN over 2H, depending on, that's why I forgot the other case, because it doesn't occur on this slide. Depending on whether n is odd or even, which is the algebras that commute with the SU2 action. So the good news is that this spectrum is the same as if you calculate the spectrum take an ordinary sphere and look at the Dirac operator spectrum, the spectrum of this Grosser-Presnada operator is the same spectrum but just cut off at some sufficiently high eigenvalue. So there's a finite number of eigenvalues that match the continuum thing and then they just stop. There's no chirality operator on this spectral triple, and that's why it's KO dimension 3. You see, for the odd KO dimension, the chirality commutes to the Dirac, so it may as well be trivial, which is like saying there isn't one. And of course, you expect the sphere to be, it's a Riemannian manifold, and so it has a little Clifford algebra at each point, which is KO dimension 2. It's a type 02. So you expect a sphere to have KO dimension 2. But if you write down a KO dimension 2 spectral triple, and then you forget the chirality operator, you just sort of throw it away, you end up in KO dimension 3. You have the same, everything else satisfied. And so what's going on here is you see a normal round sphere, of course, has a Clifford module every point, but the bundle is K, it's non-trivial. And the chirality operator would split the spinors into left-handed and right-handed spinors, and they're non-trivial bundles. So you couldn't describe it in this framework with global spinors. So if you glue the bundles back together, then the spinors are, again, trivial. And so you can think of this construction here as what would happen if you put the two-sphere into flat three-dimensional space, and then just use the three-dimensional spinors from the ambient three-dimensional space. Of course, they have the same dimension, but what's missing is the chirality operator. So the fact that you've gone to the global spinors means there's no chirality operator. So this example, while it's very instructive and very successful, it's somewhat defective in this sense. Okay, so how am I doing? So now the first attempt, perhaps a bit naive, to remedy this was the doubled sphere. And so now I double the size of the spinors. I have C4 spinors. And you just simply take the, as a new Dirac operator, the sphere Dirac operator, a 2 by 2, block 2 by 2, using the old Dirac thing that I had before. So this is now respects the chirality operator, gamma here, which means the first two components are the left-handed spinors and the second two components are the right-handed spinors. And you see that ds anti-commutes with that, which is, hooray, what you want for an even real spectral triple. And so the KO dimension is now 2. And we've restored, hooray, we've done it. But it's sort of cheated, because what you've done is, because the chirality operator is -1 on the bottom entry there, what you've done is you've taken 2 copies of my old bundle and reversed the chirality of the second copy. And then when you glue the left-handed or right-handed spinors together, you have a left-handed spinner from the top copy and then the right-handed spinners from the bottom copy, and they glue together and make a trivial bundle. So both the left and right-handed spinners in this doubled sphere are trivial bundles, and that's why the matrix thing works, you see. So the spectrum is again a doubled S2, but cut off. There's twice as many eigenvalues. And just a note for later that you can, of course, use the unitary operator very simply sort of diagonalize, in a sense, the 2 by 2 matrix and have dGp and minus dGp, the cost of messing up the chirality operator. Okay, so that's the doubled sphere. Okay, so now I'm off on my sort of deviation track a little bit, but I think that's important. I've got, yeah, right. I want to talk about the spinor bundles. So this is a construction due to Grosser, Klimczyk, and Presnado in '96. So you start off with a Hilbert space of 2 harmonic oscillators. And then in this, there's a number operator. It counts the number of both particles and added together. So that's A1 star A1 plus A2 star A2. And I'm going to write that as AI star AI. So there's an Einstein summation convention over the I index going from 1 to 2. So that's the number operator. And then if that has a distinct eigenvalue, then that defines yourself a finite dimensional subspace of the space of 2 oscillators. And that's, in fact, an irreducible representation of SU2. So that's the well-known harmonic oscillator representation of irreducible representations. So I'm going to call that thing Vn, that subspace of harmonic oscillator. So it's the harmonic oscillator subspace with n particles. Now the Hilbert space for this this attempted spectral triple has got a left-handed part and a right-handed part, and the left-handed part is Vn tensor Vn plus 1, and the right-handed part Vn plus 1 tensor Vn. So they're almost square matrices, but not quite. They're slightly rectangular matrices because one is n and the other is n plus 1. And then the Dirac operator is a simple formula which is written in a 2 by 2 matrix form where the top row, the top part of the vector is h left and the bottom part is h right. So the little d takes you from Vn tensor Vn plus 1 to the second factor, Vn plus 1 tensor Vn. And the formula for it is written there. It's AI star tensor AI. So the AI is the creation operator for the harmonic oscillators. So it adds one particle into Vn, taking it up to Vn plus 1. And the AI destroys a particle. So it takes the second factor Vn plus 1 down to Vn. You see, so one goes up, one goes down. And that's how that works. Okay, so there's the operator D going from the left fermions to the right fermions, and D star, as our joint, goes back the other way. So you package them both up in a 2 by 2 matrix, call it big D, and that's my Dirac operator. And with the chirality operator as obviously here, 1 for the left-handed and minus 1 for the right-handed, then this has k dimension of 2. So, hooray, we seem to be back on track, and now we've actually got spinor bundles, and if you kind of think about the representation content of these things, it's what you would expect for, so if you take Vn tensor Vn plus 1 and take the limit, or induced limit as n goes to infinity, then that becomes the representation content of the sections of a left-handed spinor bundle on an actual regular sphere. So group theoretically, it captures the whole thing with the topology and all. But we have a real structure here. J is the charge conjugation on each space and then the flip map. So obviously it takes you from the left-handed fermions to the right-handed fermions. So anti-commutes with chirality, so on. We have k dimension 2. So perfect. And the spectrum, again, you can compute is the cutoff 2-sphere Dirac spectrum, also perfect. But here there's no algebra. you see the algebra sort of got lost because now the space is that there's the algebra matrices in Vn, but there's also the algebra matrices in Vn plus 1. And if you had both at once, that would be sort of too big, you see. It would be like trying to describe two spaces. So that's sort of where that was and was left. It's somehow successfully described non-trivial spinor bundle, but we've lost the spectral triple bit. Okay, so now here's my new piece, which is what I'm giving you as something this afternoon's news, if you like, is if you take this Dirac operator I've just constructed, and I form the direct sum with a slightly smaller one. So I put the subscript n-1 to mean the same construction as on this slide here, but instead of n, everywhere I write n-1. So I direct sum the Dirac with minus the slightly smaller one, which I can write in my 2x2 matrix notation there by putting in each entry d tensor, well, and the bottom left entry, d direct sum minus d star n-1. So I've interchanged left and right for the bottom one, much as I did in my cheat bundle construction. And then again in the top right-hand corner, that's the adjoint of what's in the bottom left corner. And it turns out, and it's quite a long calculation, but quite fun to do, that this is unitary equivalent to the thing I called the doubled fuzzy sphere before. So if I go back to this doubled sphere here, ds here, and now here both DGP are both the same size matrix. So there's some unitary operators, alpha and beta, which you can put together, and this is the old double spinor thing. So you see, and you might ask, well, okay, well, what are these maps alpha and beta that do this unitary equivalence? Well, it's sort of instructive to see what they are. I've written alpha, and the D, the left-handed spinors for that live in Vn tensor Vn plus 1, but the right-handed spinors for Dn-1 live in Vn tensor Vn minus 1. And so on the left, on both things, we've got Vn, that's fine. But on the right, we've got Vn plus 1 direct sum Vn minus 1. And there's a Clebsch-Gordon series that you can direct sum those together to give yourself Vn again, but tensored with a two-dimensional space, which is, of course, V1, the representation of spin half. And so now, having done alpha, and there's a similar formula for beta, the algebra, which is the endomorphisms of Vn, will act on everything, you see. But only after you've done the isomorphism. So we can reconstruct everything we want to know about the spinor bundle by going to this trick of sort of straightening it back out again, doing the operation there, and then wondering what happens when you transport it back into the curved bundle land. So the algebra action is a complicated thing to work out, but here's the formula for the fluctuations. So if I have a set of matrices in my algebra here, which is the algebra of the endomorphisms of Vn, then the fluctuation sends the sphere Dirac operator to itself plus f plus some conjugated piece. And there's your formula for f. So interestingly, you start with what's almost the Dirac operator. There isn't a pointer here, is there? Well, when I pressed this, it changed the slide, so that... What do I... On here?
This one.
Oh, it's that one.
Yeah, that one. Yeah.
Oh, I hold it, perhaps. That's my mistake. I didn't hold it. Right. Okay. Thank you. Yeah. Okay. So, so this is almost but not quite the Dirac operator you started with. Here's my algebra elements that are part of the fluctuation, and here the Li are the corresponding are the Lie algebra generators in the representation that they need to be in to work on the various spaces. You see, because whoops, you're right. That's the problem. Yeah, if you don't hold right. Okay, so and then there's the commutator here with this Lie algebra thing. So it's sort of like the Grosser-Presnada operator, where you have some arbitrary thing here, and then these are like trying to be the Lie algebra generators or the gamma matrices or something. It's a bit complicated, but anyway, that's the formula. And in here, these iotas there's a natural injection operator that takes you from the slightly smaller Hilbert space to the slightly bigger Hilbert space, and it commutes with the Dirac operator. So it's an intriguing formula, and I don't claim to understand everything about it, but if anybody would have any ideas about how to interpret this formula, that would be great. Okay, so I want to leave that behind and talk about the deformed fuzzy sphere just for a minute, just to show that we don't always have to be doing round things. So this is the same formula as before, except we've put in arbitrary constants A0, A1, A2, and A3. A3 is 1 minus A1 minus A2. And then A, you can't see very well, but that axis is A2, and that axis there is A1. And what we've plotted here is we've taken this spectral triple with this deformed Grosser-Presnada operator here and calculated the spectral variance, which you can think of as the heat capacity of a fermion. You know, when you do elementary physics, you learn that the heat capacity of an ideal gas is the gas constant times 3/2. So you learn that when you're this big. And the 3 is the dimension of space-time. So you can use the ideal gas as a dimension detector. And so we do the same thing with the fermion here. We work out the heat capacity, and that's called the spectral variance. And so it's a function of the spectrum of the Dirac operator. And so here it is plotted as I deform these parameters, A1 here and A2. And the boundary of this thing is, of course, where something degenerates, becomes 0. And what you see here is that the vast majority of this plot is this nice sort of pale blue color, which is around this value 2 here, which is the dimension of the sphere you expect. So what it's telling you is there are nice manifolds where you deform the parameters here. This A0 here has to be calculated in the right way. It's like cancelling off the torsion of the Dirac operator. But when you insert the right value for A0, then you get this nice plot. So there's a secret formula for doing that. And the data visualization was done by my MSc student, Qi Gong, so thanks to her for doing that. Okay, so quantum gravity. So here's what we want to do. We want to calculate a partition function by integrating over spectral triple data. So D is the Dirac operator, and it turns out for finite spectral triples, these live in a vector space. So all the constraints on the Dirac operator are linear. So there's a vector space of Dirac operators. So we integrate over this vector space. So that's the bosonic integration. And then the fermionic integration is here. We look at the vectors in the Hilbert space and do Grassmann integration. They're promoted to come up to a Grassmann algebra, and you do the right thing for fermionic variables. And in fact, what we do here is entirely H+, so the left-handed fermions, as I wrote in the previous slides. So this is how you do a chiral functional integral. You only integrate over the left-handed fermions. And physics, as we know it, is chiral, so you have to be able to do a chiral functional integral. And so this is for Euclidean quantum gravity. There's e to the minus action here, and there's I times the Euclidean fermion action, which is psi bar d psi, but with a j inserted in the angle brackets is the Hilbert space in a product. So inserting a j in the left-handed slot makes the whole thing bilinear, which means that the whole formula only depends on the fermion field psi and not on its conjugate field. The complex conjugate drops out of this formula. So this integration is only over d psi. So it's like a sort of contour integration in complex variables. We integrate over dz, but you don't integrate over dz bar because nothing depends on it. It's just like that. Okay, and the idea is that for Lorentzian quantum gravity, we're supposed to rotate the contour of integration in the complexified Dirac data, G tensor C. And this will take us to Lorentzian Dirac operators. That's the idea. A certain amount about this is understood and well understood, and it's a whole lecture. If anybody's interested, please go on YouTube and find my GGI talk on this subject. There will be a paper eventually. One of the things that's understood very well.
Important big rotation. Can you explain a little bit more? So the script G is collection. Okay, the collection of Dirac operators.
Collection of Dirac operators. Yeah.
How you rotate them?
You have to rotate in the complexified Dirac operators. So some of the components become complex when you rotate to another contour in which some of the components of Dirac are complex, but you then reinterpret it in terms of the data for a Lorentzian Dirac operator.
And C is just the value of the
C is the complex numbers. Just
which is part of spinor.
No, it's just the complex numbers. So one thing we do understand well is that this fermion action becomes the correct Lorentzian fermion action when you do this process. That's well understood. Rotating the bosonic part is a little bit more heuristic because of the conformal contour rotation business and so on. But anyway, that's, as I say, it's another whole lecture. So here's an example we computed with a matrix geometry model. This is the type 2-0 matrix geometry model. So remember that it has two anti-commutators with Hermitian, random now Hermitian matrices. And we put in, as an action, the trace of a potential, and the potential of the Dirac is d4 plus some coupling constant, g2 times d squared, which means that the action is just the sum over the eigenvalues of lambda fourth plus g2 lambda squared. And of course, the interesting g2s are the negative ones, because that's like a Higgs potential. Here's the picture of the potential up here. Different colors for different values, negative values of G2. And as you make it more negative, the well gets deeper, so the yellow one is a nice deep well. And then you see in the corresponding here what the eigenvalue distributions are when you do this integration over Dirac operators. And we did this with Al-Glaser back in 2016. And we discovered, as you might expect, well, after you've done it, you might expect that, of course, the deeper this potential well is, the more the eigenvalues try and fall into the non-zero points in the potential. Whereas for the shallow potentials, they'll be spread evenly because eigenvalues repel in the matrix model, remember. But when the potential gets big enough, they fall into the well, and you get a phase transition. So these are the colors here for the shallow potentials in which they're distributed right through the middle. And then at the phase transition point, the eigenvalues start to fall into the two peaks on either side here with the two wells. And the point at the phase transitions, this nice blue curve there, is the eigenvalue distribution for a Dirac operator of some finite dimensional space. Okay, and as you go away from the phase transition, the apparent dimension of the space gets larger and larger as these curves sort of bottom out and the well empties out in the middle there. Okay? So the picture is a phase transition, and at the critical point of the phase transition, you get a nice curve. Thank you. So that's what we found. So what my student Mauro D'Arcangelo found looking at some more models, he looked at some type 3-0 models and the type 0-3 model. So the 3-0 model has one commutator and 3 anti-commutators, and the 0-3 has one, like the fuzzy sphere, has one anti-commutator and 3 commutators. And you need to remember to the next slide this decomposition. A matrix will be decomposed into T, the value of its trace, and V, the trace-free parts of the matrix. So here are some results. So firstly, the type 3-0, the one with 3 anti-commutators. This is sort of the power, basically, in each of the types of matrices. I'll try and read it off. The first one here, the pink ones, is T1 squared plus T2 squared plus T3 squared. And you see here that for small negative G2, essentially there's nothing going on, and then you reach the phase transition, and then those values rocket. So that's an order parameter for the phase transition, which is second order here. And then the other colors are the power in the other matrices, and they don't do so much. So what you see after the phase transition is that if you plot the values of T1, T2, and T3, as you do on this graph, the axes of T1, T2, and T3, they lie nicely on the sphere, and the dots are different instances taken from the ensemble to plot the points there, and they sit nicely on a sphere. So what we see here is that after the phase transition, we get a commutative sphere. Here's an example of type 0-3, where what happens is that all the power stays in these blue dots, which are the trace of the sum of squares of the traceless parts of them. So all the power is in the traceless parts of the 3 matrices that go into the commutators here. So if you like, the derivative parts. And the amount of stuff in the others is negligible, except perhaps here where something possibly went wrong with the computer calculation. Not sure. But anyway, so if you look way past, if this is a phase transition here, you look way past it, what you find is that everything is dominated by the traceless parts of the matrices. And if you rescale them with some parameter, they approximately behave the commutation relations of SU2. And in fact, if you calculate what for SU2 you expect the trace of V squared is, you expect it to be G2 over minus G2 over 16, and you look numerically, it's almost bang on exactly. And then if you take a given matrix, say V1, and you plot its spectrum, you see nicely integer-spaced eigenvalues, which is exactly what you expect for the spectrum of a generator of SU2. So this is strong evidence, and there's more evidence in his thesis, that what's happening here is that after sufficiently large matrices, when the wells are sufficiently large coupling constant, when the well is quite deep, it's forcing it into a fuzzy sphere. So you have a fuzzy vacuum, if you like. My final topic is on fermion integration. And here's a formula which I discovered in investigating this. If I start with a spectral triple of KO dimension 4, and I double it, much as I was doing earlier, you get a KO dimension 2 spectral triple. So the Hilbert space is doubled, the Dirac operator is like this, where gamma is the chirality and mu is a parameter, and real structure. Then if you calculate the fermion integral here, with the Euclidean fermion integral type, with the chiral one, so psi are only in H+, the left-handed fermions, you get this nice formula here involving the fourth root of the determinant of d squared plus mod mu squared, should be a closed bracket at the end there. And this correction term is a phase factor to the power of the index of the Dirac operator. So in fact, e to the I theta is, I think it's I mu over mu bar, something like that. So this formula really should be in the physics literature somewhere. I mean, I'll be absolutely shocked if it isn't, but I haven't been able to find it. An interesting project. But the possibly more important point is this only works with these KO dimensions. All the other ones are either zero, trivial, or ambiguous. There's some phase which is ambiguous and not defined. So my final slide here, some applications of this. As I said a long time ago, if you integrate over one generation of fermions, you get an induced bosonic action, which is induced standard model action, which is perhaps something a bit like what Walter was saying today in a slightly different setting. And Christoph Stefan said the same similar thing. Is he here? He's supposed to be at the conference. He's coming, right. He gave a talk many years ago about this, and I thought the slides were on the web, but they disappeared. So I'd really love for him to recover that and to see what he said. Or, more physically perhaps, if you just integrate over the right-handed neutrinos, a similar thing happens. And my student, Alex Nagan, is putting this in his PhD thesis. It's been examined, so it'll be out very soon. And finally, you can put the fermion integral into the Dirac ensemble and play the same game as I did with the random Dirac operators, but with the Dirac action, with the fermion action as well. And this is what Masood and his collaborators have been doing recently. Okay, so I'll stop there.
Thank you very much, John. Quick comments, questions, remarks, please. Yes.
You said something very interesting about Lorentzian to Euclidean quantum gravity.
Yeah.
And usually in quantum field theory, we have the Osterwalder-Schrader reconstruction theorems that put you on puts one on a sound footing, which allows you to at least rotate the correlation functions. You have a partition function, and presumably you can also compute correlation functions. So do you see that? Do you see somewhere the analog of Osterwalder-Schrader?
No, it's not the same thing. Weak rotation is not the same thing as contour rotation. This is contour. This is rotation of the contour in the space of geometries. So there's no correspondence between the geometries, Euclidean geometries, and the Lorentzian geometries. Whereas in weak rotation, you start with Euclidean geometry and turn it into a Lorentzian geometry, or vice versa. But that's a different story. But I should stop, right?